Thank you for the introduction. Raymond Wilson. I'm a Trimble Distinguished Engineer with Trimble, working in the construction division. My presentation...
Sorry, it was just a fast start because it went several seconds to go on stage, so please start from
okay. You want me to just start now, is that correct? Thank you for the introduction and the opportunity to present at the summit today. So I'm Raymond Wilson. I'm a Trimble Distinguished Engineer, and I work in the construction division of Trimble. And in today's presentation, I'd like to go over our experience in our project building our geospatial analytics platform for our construction productivity project. In terms of where I am, to explain the funky accent, I come from Christchurch in New Zealand. This is a lovely view of the South Island taken from the International Space Station. In terms of an agenda, I'd like to cover some background about what it is that this product does and the reasons for it, why we chose Ignite as a platform technology, the architecture behind some of the key aspects of it, and I'll also cover a collection of tips and learnings that we made in the process of building it, and then finally cover some operations and deployment topics. For our background, I'm talking about a project we call TRex, and its aim is to replace a custom in-house memory-centric data grid that we built to support our construction analytics product. There's some further background. Construction as an industry is going digital. The days of paper plans are mostly gone, especially in the Western world. And it's been a fact that the construction world has lagged in terms of technology. And that's no longer the case. Designs are now commonly digitally prepared and sent to the field to be built using machines, using machine control technology. And that data covering how they are building those projects, how those earthworks and compaction processes are being performed by those machines, is sent back to back office software. And this is really the last mile in terms of closing the construction technology loop for customers. Now we have some software and analytics platforms that are giving our customers insight into how well their projects are being built in terms of productivity and quality and cost. When I speak of a project in the construction world, they can be widely varying. They can be very large. The picture on the right is really showing an elevation thematic map for a project that spans about 24 square kilometers. So they can be really quite large, but they can also be very sparse. The colored areas are the only areas in the project that actually have data. And they can also operate for very long periods of time. And apart from that, they combine many disparate sources of data, and that can include final designs. These are the things being built. Imagery that's been collected by drones or unmanned autonomous vehicles. Various different topography sources such as LiDAR or photogrammetry or traditional survey processes. And then also the data that's been collected by the machine control systems and repatriated back to those backends in terms of what we call as-built and productivity data. So Trimble Works OS is our client-facing product that provides geospatial analytics for construction projects. It provides a whole variety of workflows to do with how customers run their projects, and it gives them insight into various analytics. They can perform spatial profiling to see if things are being built correctly, perform volumes calculations, reports, exports, and various other metrics. What is supporting those workflows in terms of capability is a geospatial platform that aggregates all these sources of project data into what are called queryable historic models. And they include all of these designs, topographic, and machine control data that I've previously mentioned. We do have an existing legacy platform. It was developed about a decade ago, and that's a long time for a software solution. We need a next-gen analytics platform, and there are several reasons for that. We need to mitigate tooling and technology drift. Some of these skills are hard to come by, and we need to maintain continuance for our Works OS product. In terms of our legacy platform, we called it Raptor. We quite like dinosaur themed project names. It's an in-house developed memory-centric data grid, and it looks a lot like Ignite. It provides a whole lot of things in terms of capabilities for our platform. It runs our ingest pipeline, it's our storage layer, it provides our querying layer. Internally, it provides cluster compute and messaging fabrics. The downside is it's the responsibility of the engineering team to build and maintain that quite large piece of functionality. And while it's capable and stable, it's old, it doesn't scale well, and it doesn't handle load effectively. And there are also some deployment difficulties with it. Beyond that, there are some legacy tooling and processes that, again, are part of this kind of technology drift. It's implemented in a system called Delphi. It targets Windows 64 web services, and they are essentially deployed to servers, and in this case, to AWS EC2 servers. It's becoming quite hard to find engineers with those skills, and in time, they may not exist. For our next-gen platform, we decided to call it TRex because it's really Raptor's big brother. Instead of building our own memory-centric database or distributed database, we decided to go and find one in the market. And Ignite was the one that we chose. The platform itself provides the same functionality, and it leverages the capabilities of the Ignite platform in order to do this. Furthermore, Ignite is not engineering's responsibility. It's a component that we brought in. So we're not responsible for maintaining an internal implementation of all of that functionality. The next-gen platform was also implemented using some modern processes, .NET Core, we're using containerization, Kubernetes deployments, and engineers with these skills are really easy to find. So why did we choose Apache Ignite and not Geode or Hazelcast or any of the other competitors? We had a set of requirements, and these requirements closely matched our previous platform. And the reason for that is that those requirements really were what we needed. So our needs hadn't changed a lot, and we were searching for a tool that met those needs. And this is a not necessarily exhaustive list of those needs. We had a CQRS architecture. We had projects that could range from up to billions of records within our databases. Obviously, there are many projects, and we needed distributed and cluster compute. Persistence was a feature of our previous platform, and we wanted that as well. And all of these other facets were in our set of requirements. Further, we had become a .NET Core C# shop, effectively. We needed to be able to integrate with those tool chains, and we needed to have access to a fairly mature C# client that was ideally open sourced. And given that we were also using containerized deployments using Kubernetes, some ability to run in that environment was also desired. Finally, we were really looking for a project that had life. It had very active community involvement. It had commercial support if we needed it, and it needed to be actively used and improved. Well, I think we hit the jackpot. When I completed reviewing of the capabilities of Ignite, the way it matched our requirements and our internal distributed architecture was just impressive. And it really validated our approaches. And for us, it was the obvious choice. Switching to look at some architecture. Really, I'm going to cover a number of assets of this. Really, to take a look at our high-level architecture, and in particular our ingest pipeline, the way we use affinity and co-location in a spatial sense, our query structuring, dealing with massive queries, and unit testing, which may seem like a strange architecture element, but we'll get there. So from a very high-level perspective, TRex is a CQRS workload. So we're talking about command query responsibility segregation. And in order to implement this, we effectively built two grids. One housed the ingest pipeline and was responsible for receiving data from the field and integrating it together with the existing content in the projects. We call this our mutable grid. And the mutable grid in turn performed a projection and injected data into what we called our immutable grid, which housed our query pipeline. And then our Trimble Works OS product used that as an API to source its data. The reason we decided to go with two separate grids here is to allow independent scaling and management of those contexts. At the time, we were a little uncomfortable with housing both of these facets in the same grid, and it just seemed easier to split them in this manner. If we look at our ingest pipeline, we're actually managing streams of ingest data from large numbers of machines in the field. Now, we don't actually use a data streamer in our solution, and the reason for that is that we're a little bit sensitive about data loss, not to the point of a financial institution, but we definitely don't want to be losing data if we have an adverse event. So we have an ingest submission service that essentially just injects that data to a buffer cache. And then there's a chain of other asynchronous activities based on Ignite continuous queries that harvest data out of those caches as it arrives, feeds it into preparation and staging services prior to an ingest processor service, analyzing that data and adding geospatial elements to the data caches that represent the data for each project. Now, today, this adds, in terms of baseline load, hundreds of millions of records a day, and we have less than 1 second latency in typical context from arrival of data in the ingest submission service and availability of processed data to queries in the front end. One of the key differences in our use case is the geospatial aspect. And we have a number of aspects that come together to achieve affinity partitioning and processing. We have we take our geospatial data elements and we aggregate them into what we call natural work units, typically about 100 meters or 10 meters square or 100 square meters in size. Each of these work units may contain thousands of records processed from the ingest data. These aggregated work units are labeled with geospatial keys. So once we've aggregated, we have labeling. And labeling is common to not only the ingest data, but also our designs and other topographical data, because this data all gets mixed together to produce the final results. And we then have built custom affinity functions to map those geospatial keys to partitions. And at this point, we've effectively defined our affinity and collocation. Now, some of our projects can be very large, and it's not unusual to see more than 100,000 spatial work units in a project. And if you go back to that project I showed with a very large extent but very sparse, those work units can be distributed widely across the actual ground that a project may occupy. Moving on, we mix in topographical data. So queries into our system are almost universally spatial, and they combine the as-built data, the design data, and topographical data into collections of work units that are ultimately submitted through a submission process into the cluster compute processing. Now, we actually have had an issue where we had extremely large numbers of these keys, and we have a very efficient key encoding mechanism. And we often take less than 1 bit per geospatial work key to represent those within a request. And those requests are then sent to the cluster compute processing layer, and that is essentially spread across the server nodes responsible for the caches holding our spatial project data. And now we have co-located processing of that data. When we start to look at the actual architecture of our query, there are two core or two primary paths that they go through. This one here is what we call an aggregating query pattern, and it's essentially a map-reduce style query. The core story being told in this otherwise busy diagram is that there's a path, there's a dance that a query goes through. And it typically starts at a web service layer, and this might be a query for something like a volume calculation. This is represented by a request compute function. It transits through Ignite. It comes through to the respective analytics service. So this will be an instance of a volume analytics service. This in turn creates a secondary argument, a compute function, and sends it down into the compute cluster. And this is the place where we have a co-located processing. And each node, which server node responsible for the caches holding the data that have been queried across, will compute their part of that and essentially return a map-reduced response for that set of data back up to this middle tier analytics service. That then performs a secondary analytics map production over that data before sending the actual result back to this web service here. Now, in this case, the response might be 3 or 4 numbers of value. And down here, it may have processed billions of records in order to achieve that single response. This dance here, which is involving 3 or 4 coordinating service layers in a compute cluster, these can take small numbers of milliseconds in some instances. This pattern here looks remarkably the same, and it is by design. The difference here is that instead of getting a very small answer, typically your answer is substantial in size, and reporting is a good example of this. This is a flow which is very difficult to use a map-reduced pattern for. And in particular, it's very difficult to use an Ignite map-reduced style API. And the reason for that is the responses themselves could be many gigabytes in size. And this can cause node failure, which is undesirable. So in this pattern here, the cluster compute nodes, instead of sending map-reduced responses, are actually sending raw processed data according to filtering and other constraints in the query up to the reporting service, which is then responsible for aggregating it together before producing the final report, which might be a CSV file or an Excel file, and then up through back to the web service to the UX context. So we talked a little bit about how some of our queries can be very large, hundreds of thousands of keys, clusters of compute nodes required to compute the responses in parallel using map-reduced paradigms. And so these really are the kind of core aspects that allow us to keep to our SLAs. Clustered co-location is very much an Ignite staple. We use Kubernetes, and this gives us a lot of flexibility for providing the right amount of resource to our platform to allow it to respond to load. And we can scale up and down very quickly in some aspects of that, and that gives us a lot of power to tune our deployment. We have some custom quality of schedule servicing. Let me rephrase that. There's some custom quality of service scheduling to prevent load-based service denial of service issues. This was necessary to retain responsiveness on our platform. And associated with that, we have highly concurrent processing with many individual processes available to pitch in onto those requests. So not only do we have cluster compute at a node level, each node essentially is its own parallel compute engine. And then we leverage the Ignite messaging infrastructure, which allows these complex interactions to occur very quickly. And the last thing to note here is that we have web API gateways that separate the Ignite grid world from the wider service platform that also is part of our infrastructure. And these provide actually quite low impedance interaction facades. Now, I mentioned unit testing, and this might seem like a slightly strange architectural topic. We run many thousands of tests for every build that we do, and builds occur all day, every day. And we like that to be fast. And creating lots of Ignites of nodes is not fast. Furthermore, if we were to mock out every structural layer, every layer of our architecture in our stack, that's an enormous amount of work. And it also builds a lot of structural fragility into the test suite. Even minor changes can cause significant rework in the mocking layers. So we've discovered that for TRex unit tests, the best way was actually to mock the infrastructure. So we have essentially mocked the entire Ignite layer, storage, compute, query, message, transaction, you name it. If we used it, we mocked it. The result is we can define unit tests and TRex that engage the ingest pathway and the query pathway in a way that the business logic is actually not aware of any difference. We can write a unit test at very high level. For instance, if I want, I can unit test a high level volume query against a known data set that's processed and then accessed through a query. And that's all achievable through a few lines of code via this mocking framework. It's been a significant journey for us in Ignite, and we've learned a bunch of things on the way. And building a simple hello world Ignite application is pretty easy, but when we start building hardened enterprise ones, we need to step back and take a look at a few other things. Serialization is a tricky one. Ignite has a really clean approach to serialization, and it's very easy to use. Once we step out into highly performant pathways and significant data storage with fine-grained records, there are some drawbacks, particularly for the .NET default serialization, which is very bloated. Ignite's also a little bit unforgiving if you change the type of the name of a type. Things go sideways a wee bit. And version management is a little troublesome. That's not to say that it can't be done. It's just that schematically, there's a bit of ceremony involved. The solution we decided to go with is really come back to a fairly closely mediated serialization using the ibinarizable overrides, just to make sure that all the persisted and transmitted in data was very cleanly serialized. And we found that, yes, it's more work, it's more code, it's more ceremony, but we got a performant, space efficient, and easily transparently versionable system, and it has predictable behavior and schemas change. And those aspects are all really valuable. We did a lot of work with thread pools. We have very high concurrent query loads. It's not unusual to see 1,000 concurrent queries hitting our facade at the same time. And even with very large public and system thread pools, say 500 or 1,000 threads, we would saturate them. Now that's okay, Ignite handles that, but saturation has a drawback, which is because of the way we have orchestrated service layers engaged in processing a query, we were running into deadlocks when logic paths would re-enter a saturated pool. And as soon as that happened, it was really game over. The fix to that is to define custom thread pools to make sure that these logic paths attempting to re-enter the same context that may have a saturated pool have their own dedicated pool to execute on. A second aspect of thread pool saturation we discovered is a denial of service issue. If we have a saturated thread pool and further requests arriving, Ignite queues those requests and waits for a thread to become available, which is great. What we have, though, is a mix of queries. Some might be slow, some might be fast. And we have SLAs that we're required to meet on all of these queries. And if the execution engine is blocked from seeing the full set of queries that have been made to it, because some are queued and some are executing, then we get issues with requests that may just simply time out before the execution engine can see them. The fix for this was more significant, and we did a radical restructure to pervasively use .NET task processing, async await, within our internal engine, and also to use what I call a two-way async pattern, where both the client and the engine are asynchronously managing their request. A client makes a request, the engine acknowledges it, and the client then asynchronously waits while the engine asynchronously produces a result and then sends it to the waiting client. In this pattern, there's no camping on threads and thread pools. The Ignite thread pools become very transient actors in that flow, and they perform very well in this structure. I talked a little bit before about our aggregating query model using MapReduce. It's great for a lot of use cases, but if we have large responses, because each compute task sends only a single response, it becomes quite problematic for large query results. And the response to that is to use a pattern that uses that progressive repatriation of portions of responses. I mentioned before we use Kubernetes, and we discovered that the Kubernetes IP finder doesn't like to find the home grid for a new node if there happens to be more than one of them. And the cause of this was the IP finder's use of a default port number with no configuration. So we essentially have a small internal branch of Ignite where we define this discovery port. I would like to contribute this back to the Ignite community so I don't have to merge it every time we upgrade Ignite. So we'll be chatting about that soon. We have what I call a dual affinity partition trap. In our mutable grid, our affinity confines all of the data for a single project onto one node. And the reason for that is due to performance. It makes more sense to process the ingest for a project within a single node rather than trying to distribute it over multiple nodes. And one of the reasons for that is if we have a failure, partial transition rollback, transaction rollback is quite difficult in that context. So the ingest grid parks each project on a single node, and then the query grid spreads the data for the projects over all nodes. And so one of my little jobs is to figure out how we can smear more of that project data into more partitions to give us a little bit more I/O performance. Node health is an interesting one. With Kubernetes, we have liveness checks. And one of the reasons for those is to determine when a node is ready to start requesting traffic. Now, an application view of liveness and Ignite view of liveness is not necessarily the same. And we can't easily tell whether Ignite thinks a node is good or bad. Mostly we suspect the node just gets kicked out of the grid if it's bad, which is one way of doing it, but difficult for other contexts. So we're looking at a more application level health notification and maintenance, so that from an application perspective, we can manage some request traffic flow and liveness issues. We've had a couple of difficulties with graceful node shutdown. That's not to say it's hard to gracefully shut a node down, but it's a little difficult to gracefully shut a node down in a way where you can ensure the node is clean. And what I mean by clean is that it has no data pending checkpointing. There is quite a slow restart for Ignite server nodes if there is write-ahead log scanning required to deal with non-checkpointed data. It would be ideal if an Ignite node, once it actually started up, had a initialization time measured in seconds when it started looking at its caches rather than minutes in happy path cases. And again, this is something we're investigating to see how we can reduce or mediate some node start times. We use AWS Elastic File Service for our storage, and there are some trade-offs there that we did take deliberately. And we initially were using 16K pages, which I reverted to 4K due to a checkpointing failure that we discovered on small data regions, which was another learning not covered here. In hindsight, this was an error, and our EFS is something like 3 times faster reading 16K blocks than 4K blocks. So we plan to move to that in the future. And as an open question, it would be interesting to know if there are possibilities to support larger page sizes in Ignite for those more latent storage layers. And a final tip, don't steal Ignite's threads. This is actually really easy to use in asynchronous programming, at least in .NET. And it's centered around the way continuation logic is handled after an asynchronous Ignite API is called. And what we saw was that an async call, such as an apply async, when it came back, we would have a Stripe pull thread come back, and we would then use that thread and execute our application logic on it. And Ignite got really unhappy about that once we hijacked all of its threads, and things didn't work very well. And the answer was to very explicitly route the continuation back into the managed C# thread pool. But that was a fun problem to solve, that one. Moving on to some DevOps and deployment topics. Five sort of little topics to cover here. We use Azure DevOps. Kubernetes is our deployment and orchestration engine. What we use for storage, logging, and monitoring. Azure DevOps is basically our CI/CD pipeline. It works really well. We have all our artifacts are containerized, and we push them out to Elastic Container Registry. And we also have release pipelines that take those containers and then push them out into AWS Elastic Kubernetes Service clusters. A build for us takes about 15 minutes, and that includes executing all of those thousands of unit tests that we talked about a little bit before. Another nice thing with EKS clusters is we can spin them up and down in minutes, and that's a very powerful tool for improving quality when your infrastructure tooling is responsive like that. Again, on the Kubernetes front, while we're .NET Core, we're actually deploying to Linux containers. Ignite runs pretty well on EKS. Once we had the IP Finder issue sorted out, we found that it's quite responsive and seems to like the environment. We also use Kubernetes to spin up and maintain multiple feature environments. And by a feature environment, essentially every pull request, every feature increment, every piece of work, every bug fix will automatically create a feature environment through our build chain. And that feature environment is a set of pods running in Kubernetes, running a set of Ignite nodes. So our number of actually running Ignite nodes may grow and shrink radically just through the working day. And that is to say, we definitely don't have statically sized Ignite deployments. Apart from that, EKS, it's fully managed, it's easy to change, easy to match resources. There's a learning curve, but it's a really powerful tool. As mentioned before, we using Elastic File Service. A reason for that is we have a K factor of 0, which is to say we don't have any backups, and there is some background to that, and that's something that actually may change. For a storage layer, fully managed, pay-as-you-go storage, it's really dinosaur killer event durability. It's pretty much S3 level. Lower throughput and higher latency compared to Elastic Block Store or co-located SSD. It's not a performance storage layer. Absolutely. And as mentioned before, bigger page sizes are better. As far as logging goes, because we use EKS and containerized solutions, it's very difficult to tail a file. Logging to a file is really a thing of the past. We use FluentD as a daemon set deployed onto our EKS clusters. That forwards log information to Elasticsearch, and Kibana is the tool that we use for log analysis and triage, which is pretty effective actually, and especially when you consider that as Kubernetes pods come and go, Kibana gives you a continuous insight to the logging out of those services. And last but not least, monitoring. We use in TRex more than 100 custom metrics today, as well as a collection of other platform metrics. Prometheus is our chosen client and server of choice for scraping the metrics. And we use Grafana to visualize those and to build alerting out on. And we support, Grafana supports many useful interactions from Hangouts chat to pretty much anything you would like. I mean, ultimately, if you don't have a comprehensive monitoring and solution in place that gives you clear and deep insight into how your platform is running, you are effectively running blind, and it's a very uncomfortable feeling. So, what are we thinking about doing next? I've mentioned larger page sizes. That's on our to-do list. Zero downtime deployments is another thing we're doing. Because we have K-factor of 0, we can't drop and bring up upgraded nodes. So it's very difficult to have a continuous workload experience in that setting. And also active node availability. And this really comes back to sort of application level node availability and health, so that from an application perspective, we can drop a server or a service node out of service and drain all the requests it's currently executing before actually cleanly ejecting that from Kubernetes. There's just not quite enough transparency about things to do that otherwise. So to wrap up, what have we covered? Well, we've looked at a little bit of the background of what the solution does and why it does it, and why we were modernizing our technology. We chose Ignite because it was just the best fit. It really was. And it's been a pleasure to work within the Ignite community. It's responsive, they're friendly, nothing's a problem, and it's been a good experience. For architecture, really Ignite is just a key infrastructure component. All the capabilities it provides, compute, messaging, storage, scalability, they all do things that we need, that we had to do before ourselves in our legacy structure, and that's been very useful. And overall, CQRS model with those separated grids. A collection of things on operations and deployment, Azure, infrastructure as a service, logging and monitoring tooling, they all come together as a cohesive whole in terms of what we do once we've written the code and deployed it. Covered a collection of tips and learnings, which I hope some people here may find useful. There may even be an aha moment or two. They're always good things to share. And we took a brief look at some of the things that we might be planning to do in future. This really covers what Ignite means for us. We get to spend more time solving customer problems and less time supporting a non-functional requirement. Now, it seems like a put down to call something like Ignite a non-functional requirement, but from the user's perspective, they never see it. It's not something they care about, and it doesn't solve their problems. So it is a non-functional requirement from a user perspective. It is a very, very functional requirement from our perspective in terms of the engineering to build the solution that our customers use. And we're now at the end of my talk, and I thank you for your time. And if anyone has any questions, I'm too glad to answer them.
Thank you for your time. Thank you for your presentation, Raymond. That was quite insightful. There are a couple of questions I want to send you away and hopefully could get some answers to. The first one is from myself, actually. How are you getting data from these systems into Ignite? You mentioned something about that at the start, but it wasn't quite clear to me how you get all of this data into Ignite.
The machine systems send, we'll call them packages of data that contain a period of time's worth of measurements, say 5 minutes. They're sent effectively through the internet to our service facade, and they are queued up and then ingested through our processing pathway. Right,
gotcha. Okay, the next question is about the query architecture diagram that you showed earlier. It had Ignite, if I remember, on the left and the right. Was that because you're using two separate Ignite clusters, or was that representation just to show that you were getting data into Ignite, back out to do some additional processing, maybe in an external service, and then back into Ignite again?
Yes, more the latter. It was the color coding, which I neglected to cover, apart from the legend on the diagram, was that everything in orange was just Ignite. These were all of the places in that orchestration of a query flow where Ignite played a part. And the purple parts were all of the pieces that were application logic, i.e. things that we had to build. And when I contrasted, if I were to contrast that with the legacy system, all of those orange Ignite parts were pieces that we were previously responsible for. And in the new system, these are the capabilities we get by using the Ignite system.
Okay, and we've got 1 minute left. I'll try and get this one in quickly.
I'm sorry, I think I ran a little over time.
No, you're within time. The last question is just on the MapReduce section of the same diagram. Are you using Ignite Compute for that MapReduce work, or are you using an external system like Hadoop or something else for MapReduce?
We're using Ignite. It's essentially an application mediated MapReduce. MapReduce is what's happening. Yes.
Yeah, gotcha. Perfect. All right, that's it for time. Thank you again for your presentation today. I'm sure it was useful to the community, and we'll look forward to seeing you potentially at the next Ignite Summit or other events.
I'd love to be there.
All right,
Thank you very much.